If it's very difficult to bring about genetic change of physiological systems as a whole, as the study on agama lizard adaptation seems to have shown, then there must be other means for adapting to the extremes of temperature that animals must always experience. So let's take a bit of time now to explore some of the ways that animals adapt to either extreme heat or extreme cold. It will be helpful if we first say something about the thermal energy budgets of animals that experience different kinds of temperature regulation. We're already familiar with some of this from our discussion of the derivation of the Scholender principle, namely that for animals with constant body temperature, the thermal energy balance comprises heat flux rates from metabolism, evaporation, radiation, convection, and conduction, all of them adding up at any time to zero. At the risk of beating a dead horse, this is required by the principle of conservation of energy. Constant body temperature, therefore, is the consequence of the balancing of various fluxes of heat into and out of the body. When it comes to adapting to extremes of temperature, this boils down to the balancing of the physiological heat flux components, metabolism and evaporation, against the physical heat flux components, namely radiation, convection, and conduction. In our previous discussion of the Scholender model, we've already covered what metabolism can do for adaptation to cold. What interests us right now is the evaporation term, because this is a major avenue of the physiological control of heat losses from the body, which is important at high environmental temperatures. Evaporation of water is a very effective means of dumping heat from the body. For every gram of water evaporated from the body at 40 degrees Celsius, 2,400 joules of heat can be removed. We're all familiar with this effect. We can feel quite dramatically the cooling effect of evaporating water from our own skin surfaces. For our purposes, we just need to remember that evaporation is the principal means of removing excess heat from the body when the body temperature is constrained and is driven by substantial inputs of heat from metabolism, radiation, convection, and conduction. There are several generic mechanisms that are involved in managing evaporative heat loss. Sweating is the one that we're most familiar with, but that actually is a rare phenomenon among animals. Sweating requires specialized and durable structures in the skin known as sweat glands, and these are rare even among the mammals. And they're lacking entirely in all the other classes of terrestrial vertebrates, as well as from all the other terrestrial phyla. For animals like these, panting can provide an effective means for increasing evaporative heat loss from the body. Technically, panting is something that is found only among mammals, but we'll have much more to say about this later. But even among animals that don't pant, there are mechanisms for advancing evaporation from the wet surfaces of the mouth and lungs. These go by various names, including gular fluttering in birds. Because evaporation is so important a means for balancing the heat budgets of endothermic homeotherms, it necessarily has an impact on the water budgets of these animals as well. Because extremely hot conditions are often found also in extremely dry conditions, this raises the prospect of some interesting trade-offs occurring between energy balance and water balance for an animal. As a consequence, adaptations involving evaporative heat losses often go hand in hand with some interesting adaptations for water conservation. The energy budgets for animals with variable body temperature are very similar to this, but now these animals have an additional term in their energy budgets, namely a storage term, S, which involves the accumulation or depletion of heat stores in the body over time. Heat storage is necessary for body temperature to change in any way. Since temperature is simply a measure of heat density, this makes perfect sense. When body temperature is increasing, heat is accumulating as stored energy in the body, in the high thermal capacity stores of body water. And when body temperature is decreasing over time, heat in these energy stores is declining. There are a number of interesting adaptation phenomena that involve heat storage. Behavioral thermoregulation, that is, seeking out favorable microclimates in the environment, are included among these. The variable body temperature is not limited to poikilothermic ectotherms, as this might imply, however. Many endothermic homeotherms take advantage of this as well. This can involve sophisticated manipulations of body temperature regulation, including hibernation and torpor. It can also involve storage of heat in the body over time, essentially buffering the body's heat load through the day and storing heat preferentially into certain parts of the body, so-called regional heterothermy. We also need to frame our discussion around the fundamental question, namely, just what are the thermal limits for life? For now, we're going to focus on the question of there being an upper limit for life, which is germane to the question of adaptation to extremely high environmental temperatures. This question is complicated by some misconceptions about the meaning of observed body temperatures among animals. If we look at average body temperatures of different kinds of animals, we see some interesting patterns of variation. Among the endothermic homeotherms, mammals typically defend body temperatures of around 37 to 39 degrees Celsius. Birds, for their part, maintain slightly higher body temperatures on the order of 40 to 42 degrees Celsius. Because the effects of exceeding these regulated body temperatures can be severe to fatal, as in the case of high fevers, the idea has emerged somehow that this represents somehow some intrinsic upper limit to the existence of life. This notion has been bolstered by observations on other animals that indicate similar upper limits of body function. Among reptiles, for example, these animals are not endothermic homeotherms, but they do behaviorally regulate their bodies at high temperatures if they can. The actual temperature at which they regulate depends upon ecological circumstances, but this can range anywhere from about 30 degrees Celsius up to about 45 degrees Celsius in the case of some desert reptiles. Insects present a similar situation. They commonly regulate their body temperatures at levels similar to that of vertebrates, but these animals also seem capable of some quite remarkable feats of temperature tolerance, with upper critical temperatures approaching and exceeding temperatures as high as 70 degrees Celsius. Many other invertebrates are similar, but these animals don't seem to behaviorally regulate body temperatures all that well. Nevertheless, invertebrates can inhabit quite hot conditions, as around hot springs, and most notably around hydrothermal vents. In these instances, they seem to tolerate body temperatures up to about 40 degrees Celsius or so. So looking at these patterns of temperature tolerance, it seems an easy conclusion to draw that there's something about that range of 40 degrees Celsius or so that imposes an upper bound to the existence of life. Insects are a notable exception, but then insects are notable exceptions to almost everything that we can say about physiology. This idea of there being an upper thermal limit to life has been knocked into the wastebasket, though, by the discovery of thermal tolerances of so-called extremophiles. These are bacteria, archaebacteria specifically, that tolerate and even thrive in conditions of salinity, acidity, pressure, and temperature. With respect to this, these creatures can tolerate temperatures up to around 125 degrees Celsius. This is obviously a temperature that is above the nominal boiling point of water, but remember that 100 degrees Celsius is the boiling point of water at sea level. At great depths, where the pressures are considerably greater than sea level, boiling points of water can be up to a few hundred degrees Celsius. So, given what we know already about how temperature affects the stability of proteins and how this stability can be improved by structural adaptations such as loading up proteins with alpha helices, beta sheets, covalent linkages, and other such stabilizing structures, this hardly seems surprising. So, we can frame the question of upper thermal limits to life in a different way. It's difficult to see any intrinsic upper thermal limit on life per se. What seems to limit life is the existence of liquid water. And if the temperature of liquid water can be extended to very high temperatures, life will take up residence there. Where there does seem to be an upper thermal limit to life, however, it seems to be limited to complex organisms. And as we shall see, this upper thermal limit seems to apply specifically to complex organisms with nervous systems, because the breakdown of complex life appears to involve some kind of nervous system failure. We'll explore this question in some detail in a little bit, because the explanation for this has a surprising connection to the tolerance for extreme cold. So, having framed the question in this way, let's now turn to an exploration of how animals, whether they be homeothermic or poikilothermic, adapt to high environmental temperature. As we've said, this primarily involves manipulating evaporation heat loss.